Welcome back. This is the second part of a two-part series on understanding forage quality. This section will be devoted to understanding the report, and then we will look at implications for how we might feed cattle, which will be the specific example we'll use for this lecture. First of all, I want to point you to a couple of publications that I've shared with you via email or via Canvas or both. One is by Dr. Don Ball and others called Understanding Forage Quality. I would like you to particularly pay attention to pages 8 through 11, but I would say that this publication, the whole thing, is one of the best summaries of forage quality that you're going to find anywhere, and I would highly recommend that you read that at some point. The other publication I have shared with you and I would recommend you reading is called Interpreting Forage Quality Reports, ID 101 in our extension numbered fact sheet series that tracks pretty closely to what we're about to go through, but we've added in this lecture quite a bit more in terms of new terms. So let's get started. First of all, a forage report may look something like this. This is a simple forage report, and this is the one used at least a few years ago by the Kentucky Department of Agriculture. And you can see two columns, and you can see several parameters on the left that we will define quite a bit more as we go through. This is a much more complex and comprehensive report. This is Dairy 1. Actually, both of these, the Department of Ag and the Dairy 1 report, were NIR analyses. But you can see that and one of the great things about NIR is that you can actually, from one scan, create or produce or measure or estimate was the right word, many forage parameters. Now, this one that we're looking at happens to be a baleage sample, so it's right about here is where we had to ask for a fermentation panel to find out pH, the percent ammonia as protein equivalent, the lactic acid, the volatile fatty acids, and so on down below. So all of the parameters above about right here, where it says chloride, are going to be for NIR. The ones below that were a wet chemistry type analyses that gave us those parameters. So we can get quite a few parameters on an NIR report. And the cost for this report was about, I believe, $25 before shipping. So $30 would get this done for a producer. When you're looking at a forage quality report, you're going to want to always work from the dry matter basis column because the moisture content in samples will vary. Now, the time that you are going to want to use the as received or as fed, sometimes it's called as fed basis, is when you're mixing rations. In other words, when it's important to account for the water that's in a bale of hay or haylage. So for our purposes, when you're talking about balancing a ration or talking about absolute requirements, we're going to be talking about, we're going to try to take it down to a dry matter basis. In other words, where the water is basically taken out of that. And that way, if we're comparing samples, we don't have to worry about, well, this one had 12% water and that one had 14%. We're going to be able to compare number to number for the same parameter. So you're going to find lots of terms on a forage report, even more than are listed here, but let's go through them. The dry matter and moisture obviously are pretty straightforward. You measure dry matter from your dryness samples and weighing it until it stops making a difference in weight. 100 minus dry matter is moisture. Crude protein is percent nitrogen times 6.25. We'll talk more about that in a moment. Acid detergent fiber, ADF. Neutral detergent fiber, NDF. Neutral detergent fiber digestibility. And then you're going to find in some acid detergent fiber nitrogen or acid detergent insoluble crude protein. Basically, you want to know what kind of nitrogen is tied up in the cell wall itself. and you're going to find minerals on some reports. All reports are going to try to estimate energy, and they may use TDN or total digestible nutrients. They may report some form of net energy or digestible energy, and they will most likely all contain relative feed value, RFV. They may contain RFQ, or relative feed quality, and we'll differentiate a little later about what those two are. And again, Bailey samples by wet chemistry are going to give you pH, volatile fatty acids, and a few other things. Now, one critically important thing to remember is that some parameters on a forage report are measured and others are calculated. On the measured side, moisture, or I should have said just dry matter here. We actually calculate moisture from dry matter. Nitrogen. We will measure nitrogen, estimate protein. We will measure fiber and estimate energy and intake from that. We'll measure fiber digestibility. We will measure minerals. We will measure pH, volatile fatty acids, ammonia in silage. We will calculate total digestible nutrients, or TDN. Every energy value is a calculated value, whether it's net energy or digestible energy. Relative feed value and relative feed quality, RFV and RFQ, are all calculated entities of a forage sample. Now, crude protein. Why is it called crude protein? Because we don't measure protein directly. We measure nitrogen and multiply by 6.25. Why is 6.25 the factor? Because protein, whole protein, is 16% in for the most part. If you want to think of that as an equation, then you've got the nitrogen in forage is equal to the protein times 0.16. That's 16% expressed as a decimal. If you want to solve or for protein, then divide both sides by 0.16, and 1 divided by 0.16 comes out to 6.25. So 6.25 times the forage in equals protein. So that's why 6.25 is the factor. And crude protein will overestimate true protein nearly every time because forages will contain variable amounts of non-protein nitrogen, sometimes quite a bit. So let's talk about NDF digestibility just for a little bit more. It's the portion of NDF lost during incubation with rumen fluid. So quite obviously, the original measurements of this are going to be wet chemistry. However, you can calibrate an NIR to predict NDF digestibility. Now, you have to specify whether that you want an incubation time of 24 or 30 or 48 hours for that number, and that corresponds to how long they leave that NDF sample in the rumen fluid. Now, an NDF digestible NDFD of 48 is going to be pretty well the max amount that you can digest from a forage. Usually we want an NDF 30 because it's important to know how much NDF digests just in over a day, because you don't want to fill up a rumen with fiber that takes 2 days to come to leave the rumen. So NDFD is usually going to have specified a number, and probably NDF 30 is going to be more useful to the producer than NDF 48. But at any rate, you get the point. NDFD is how much of the total cell wall is lost during incubation with rumen fluid. And which reminds me to make a point that if you are sending samples off and getting this number run, NDFD, always send samples you want to compare to the same lab, because obviously rumen fluid varies with lab because they have to get it fresh from a cannulated animal. So therefore, the NDFD is going to be, you can compare NDFD numbers better between laboratories than if you, within the same laboratory than if you sent that sample to 2 different laboratories. Again, NDF-D is a measure of the digestibility of the cell wall. It's important for calculating rations for high-producing livestock, and as you'll see later, it's important, and we have to know it, in order to calculate relative feed quality, RFQ. So let's get into those relative feed terms and talk about them. We've been using relative feed value, RFV, for almost 40 years or so. It does take into account digestibility and intake using simple equations, and it's calculated so full bloom alfalfa has an RFV of 100. It's only for comparing similar forages. Another way of, well, you'll find out if you do very many of these that legumes have an inherent advantage and will always be higher in RFV at the same fiber level than grasses, same ADF level than grasses. We calculate it using ADF and NDF only, using simple equations. DDM, which is digestible dry matter from ADF, and dry matter intake, DMI, from NDF. The target, if you're going to say what is a good forage, you're going to say over 120 for legumes and above 90 for grasses. 90 to 100 for grasses is really, really good for us, for most of the hay that we make in Kentucky. And here is the equation for relative feed value. RFV equals digestible dry matter times dry matter intake divided by 1.29. And if you think about this just a little bit, this is really a logical equation, because you've got the intake, which is important to know, times how much of that you have eaten is going to be digested. And that tells you then basically, you know, the intake of digestible dry matter. So if it's 60% or 50% digestible and the intake is, they eat 20 pounds, then that's going to be 10 pounds of ingested digestible dry matter. Now the 1.29 is the factor that is used so that full bloom alfalfa comes out to have an RFV of 100. All right, let's move on. Let's take a look at relative feed quality. Now, relative feed quality is a much newer term, and in fact, it reminds me that I will also provide to you a Popular Press article that goes into the difference between RFV and RFQ. It is a true one-number comparison of forage quality across forage types, so you can compare grasses versus legumes, for example. It's improved over relative feed value because it uses a summative TDN equation for digestible dry matter that takes into account non-structural carbohydrates and the digestibility of protein and other components rather than just taking ADF alone. And it better accounts for differences in forage digestibility in that it uses NDF-D and also NDF crude protein, which is the nitrogen tied up in the cell wall, to calculate dry matter intake. Here is, and you'll notice this equation looks similar to RFV, excuse me. The RFQ is equal to digestible DMI, the intake calculation, times TDN of this summative TDN equation divided by 1.23. That factor 1.23 is done so that the range and the values are going to be comparable in terms of magnitude to relative feed value. And I want to remind you of a few things as we move on then towards interpretation of how to feed this material. The fiber goes up with plant maturity. So as growth stage goes from vegetative to bloom, the fiber and lignin go up. And of course, that means we know that the things we want, like protein, leaves, minerals, digestibility, which is not plotted here, they go down. This happens to be an actual plot of the Kentucky Department of Agriculture equation for predicting digestible dry matter, or TDN, which they use. We use interchangeably a lot, and they do as well, between ADF and TDN. And you can see that ADFs for a good forage would be in the 30 range, and that creates a TDN of about 65. Down to 40, which creates a TDN right at about 58, which is roughly maintenance for beef cattle, maybe a little lower than that. And then we see a lot of our grass samples with ADFs between 40 and 50, sometimes higher. And then you get into a range of energy here that is going to be just barely enough for a dry beef cow or other types of animals at maintenance. But you can see this is the type of graph you would get, or the type of relationship you'd have between ADF and energy if you use one of the simple equations, and the Department of Ag uses one of those to estimate their TDN or digestible dry matter, depending on how you use the term. In this case, we're going to use them interchangeably. Now, if you know, it's important, I should just start this way. It's important to know how your lab, the lab you're using to measure a sample, calculates TDN. This happens to be a listing of several labs that are commonly used. We use Dairy One quite a bit. You can see Dairy One is not there. They have not shared that equation with us, and we'd very much like to know what it is. You can see that there are several equations that just use ADF, and you can see the equations that use combinations of, that are using things that are more than ADF. Arkansas, for example, uses protein and ADF. Cumberland Valley, and this is the Ohio State laboratory. I think it's the Animal Research at Ohio State, uses what we call a summative equation, and it's quite complex. Now, I don't for a minute expect you to memorize anything like any of these equations. All I want you to realize is that it is very complex about how TDN is calculated. Now, if we were to plot a number of samples take a number of samples and send them to all these labs, the TDN numbers are going to vary, but they're not going to vary a lot. In other words, low ADF or low fiber is going to give you high energy, high TDN, no matter if you're using a simple equation or a complex one. And I took the time to go ahead and pull out that OARDC equation and put it here so that you can see exactly how complicated it is and the things that you've got to measure in order to use this equation. Now, the good thing is that you can do this with NIR. You can, once you calibrate an NIR with a summative TDN for a summative TDN calculation. Now, it takes a lot more wet chemistry to make that calibration done, to get the calibration done. But once you do that, then you're able to then predict a summative TDN from one scan of a forage. So what's important to remember here, TDN can be calculated simply from ADF alone or more complexly using the summative equation. Now, I'd like to spend the final part of this lecture talking about what happens when you hand a forage analysis back to producers. And that's exactly what you see here. These are producers in Southwest Missouri who have gotten a printout that I've just run from the mobile testing lab at the University of Missouri. Now, one of the things that I discovered really quickly is that I thought I was mostly done when I handed them the report. That was wrong, because once I handed them the report, they looked at it, then they handed it back to me and they said, well, is it any good? So one of the great lessons I learned right away is that forage analyses take some interpretation. So that's why I wrote that ID 101, Interpreting Forage Quality Results, and that's mainly from what I learned in experiences like here in Southwest Missouri. In that ID 101, the punchline, the take-home message is right here. Once you know the crude protein and the energy for a sample, then you know a lot about whether or not it's going to be adequate or not for the production that you're going to want to try to get out of cattle. This you can tell this is done some time ago, because a 1,000-pound beef cow was something more in the norm, but a 500-pound medium frame steer is still relevant. And these numbers actually don't change that much for a slightly larger animal. So we've got production stage from dry second trimester all the way up to mature and a heavy milking cow. Production needs for TDN here and crude protein. Now I graphed an alfalfa sample for this example, and that had 19.2% crude protein, 61.2% TDN, which is a pretty good sample of alfalfa hay. And you can see that dry cows only needed about 7% crude protein in their diet, up to about 12 for this mature heavy milking cow. This alfalfa sample greatly exceeded that. But in terms of energy, we pretty well finished out here at a 2-year-old average milking, or 2-year-old, or a first calf heifer here, trying to grow, to rebreed, and also milk and raise a calf. And that's a challenging animal to feed in the first place. So that very good sample of hay was not limited on protein, but it was limited on energy. And you'll see the same thing with a medium frame steer. The protein was enough to take care of gaining 3 pounds, almost 3 pounds a day. The energy was only adequate for just over 1.5 pounds per day. So if we're feeding this to a steer, then energy is limiting, which is what we said, and that limiting to gain only about 1.5 pounds per day for this steer. So this is a very simple way to let yourself know, or let a producer know, how their forage is, and if it's any good or not. And I can't tell you how many times I took a forage analysis and took those two numbers, protein and TDN, and drew them on this graph and said, okay, then we won't have to supplement with protein. We will have to supplement with energy. Now, a more accurate and a more comprehensive way to determining supplements for beef cows is one I want to share with you next. This is actually an online tool, the UK Beef Cow Forage Supplement Tool. You can get to it if you simply Google it. You can actually run it from your cell phone if you want to, and I've done that before at a field day. And you're going to come up with a screen that looks like this. To use it, you're going to need to fill out the right-hand side, the dry matter from the forage, the forage analysis, the crude protein, the NDF, and the TDN, and then list the stage of lactation. I believe that this model uses a 1,250-pound beef cow as the standard animal to feed. So let's take a look at a couple of these. Let's take a look at the forage first. It was 85% dry matter, 12% crude protein, 64 TDN, and 64% NDF, and 47% TDN. So we're looking at a pretty mature, low energy forage here. And it actually was a real forage sample. So don't get confused that we've got a 12% protein but low fiber. This was a real sample. And it points up the fact that forages, again and again, will have enough protein but will not have enough energy, and will have so much fiber that intake is limited. So in this case, we ran the results for a mid-gestation cow, which is that cow with the lowest nutritional needs during the year. And so here are the calculation results. So if you read this, we expect the daily intake of this forage for a 1,250-pound cow to be 1.88% of body weight, or 23 pounds on a dry matter basis, or 27 pounds on an as-fed basis. So here is where the as-fed basis comes into play. If you're actually weighing feed and taking it to something, then knowing what the as-received or as-fed, this is going to tell you when it gives you that as-fed, that means it's going to take 27 pounds of hay as it is, 23 pounds of dry matter, but 27 pounds as is. And then it calculates you have to pick in the model what you're going to supplement with. This is going to take a little bit of corn and a little bit of soy hull to a 1-to-1 soy hull corn gluten mix to meet the needs of this dry cow. So this forage is poor enough that we needed to have a little bit of energy and a little bit of in energy in the form, mainly this is what this is for, is a little bit of supplementation to get this energy need met. This is going to be the only thing I changed here. Oops, let's go here. Okay, so there, the forage analysis, same thing right there. Mid-gestation. Now, if you go change to late gestation, let's take a look at what happens. So we go from needing a little bit of corn, a little bit of soy hull, corn gluten. Now that's mid-gestation up to late gestation, 2.5 pounds of corn, 2.5 pounds of the soy hull corn gluten mix. And again, because of the forage, they are limited in terms of intake about what they can eat. So we're having then to add more supplement when they get closer to calving. And then at lactation, corn alone is not going to meet the needs here. We're going to have soy hulls and corn gluten, and then to meet the needs here. And we're up to 7.5 pounds a day. So again, I want to talk about the fact that if we're going to then know if we've got good hay or not, or good forage or not, the ultimate measure of quality is animal performance or body condition. And I want to use the feeding in the winter of 2019-2020, actually 2018-2019. No, 2019-2020, which would be the winter before, 2018-2019. My bad. The winter before this one, which was our winter this year, was not terribly cold and wet and damp and problematic. But the winter before, 2018-2019, we had mature hay, we had mud, and we had cold, rainy conditions. In other words, it wasn't freezing, it was just cold and rainy. So I want to introduce you to a concept here called thermoneutral temperatures. So let me tell you what happened with the cattle. What happened was we actually lost cows due to starvation. In other words, they had eaten their fill of forage. They were full, but they were actually had starved to death with a full rumen or a full GI tract. And that is, it really snuck up on people. And what they did not observe, at least in my estimation, is that the body condition of those cows was getting worse and worse. In other words, they were getting thinner and thinner. And just putting more hay out in front of those cows did not help them make up that body condition. And it has to do with something called thermoneutral temperatures and energy needs. And this is the point, that and thermoneutral is the temperature at which a cow or any other livestock does not have to expend energy to maintain their body temperature. When a cow has a winter hair coat on and it's sunny and dry, their thermoneutral temperature can be as low as 18 degrees Fahrenheit. 18 degrees Fahrenheit, quite cold. When it is wet and their hide is wet and they're out in the rain, that thermoneutral temperature rises to 55 degrees. And we know that every 10 degree Fahrenheit drop below the thermoneutral temperature, that it takes 5% energy, 5 units more of energy units per 10 degree Fahrenheit drop. So we had plenty of days that were 38 degrees or so, say 35 degrees or in the low 30s, but rainy. So that's 20 degrees Fahrenheit below the thermoneutral temperature. That means if a dry cow needs 50% TDN feed in order to meet her nutritional needs or energy needs, she'll need 60% TDN to meet her nutritional needs. So what happened in the winter of 2019 was we had cold, wet, rainy weather. The mud actually makes that worse. It takes more energy for them to move through a muddy feeding area. And what ordinarily would have been adequate in terms of hay quality was not. And animals lost body condition, which caused us a myriad of problems. So If your hay even is just cow hay, you still need to test it to know how good or bad it is. And you would be surprised at how variable hay can be, even hay that people say is probably not very good. So let's summarize these two lectures. The ideal forage is going to be leafy and green and immature with high protein and high energy. It's going to be palatable. It's going to be digestible. We're not going to have foreign material, and we're not going to have toxic plants. The ideal forage is going to have low ADF and low NDF. It's going to have high crude protein and high relative feed value and relative feed quality. And the bottom line is that forage quality is determined by whether it meets the needs of an animal to be fed. Thank you very much. So this brings us to the end of forage quality. We'll see you next time.